a gentle exploration of the universe's final chapter. This is a journey through deep time where change happens slowly and predictably. There are no sudden shocks waiting, no urgent revelations, only the steady, inevitable unwinding of everything that exists. This is a story told in the language of geology, astronomy, and physics. It moves at the pace of erosion, of orbital decay, of cooling stars. The narrative unfolds across timescales so vast that human anxiety dissolves into insignificance. Each moment in this journey has already been written into the fundamental laws of nature. There is comfort in knowing how the story ends. The universe does not collapse in chaos or terror. It simply grows quiet, then still, then silent. This exploration serves as a meditation on impermanence and the deep peace that comes with understanding our place in the longest story ever told. The format is simple and predictable. Each chapter marks a point further into the future, a milestone in the slow transformation of everything. The repetition creates a rhythm, a gentle pulse that guides the journey forward. There is no need to stay alert for surprises. The universe follows rules, and those rules lead inevitably toward rest. This video offers something rare in modern content: permission to let go, to stop anticipating the next shock, to simply exist alongside information that asks nothing urgent of the viewer. The cosmos will do what it has always done, with or without observation. Understanding this process can be deeply calming. In 1,000 years, the familiar structures of human civilization will have begun their slow return to the Earth. Modern cities, built with steel and concrete and glass, were never designed for millennia. Without constant maintenance, these structures respond to gravity, to weather, to the patient work of chemistry. Skyscrapers develop cracks as their foundations shift. Water seeps into those cracks, freezing and expanding in winter, gradually widening the fissures. Glass facades fall first, shattering onto streets that have already begun to buckle and split as tree roots work their way through asphalt. The process is not violent. It unfolds with the steady patience of natural forces. Bridges lose their integrity as steel reinforcements rust and expand, cracking the concrete that surrounds them. Without humans to clear vegetation, forests reclaim suburbs. Vines climb walls, their roots working into mortar, gently pulling brick from brick. The transformation happens too slowly for any single observer to notice, but over centuries, the balance shifts. Nature does not attack human structures. It simply continues doing what it has always done, and human construction proves temporary in the face of that persistence. Meanwhile, something subtle occurs in the night sky. The North Star, Polaris, has served as a navigational constant throughout recorded human history. Its position appears fixed because Earth's rotational axis points nearly directly at it. But Earth's axis is not truly fixed. It wobbles slowly, tracing a circle in the sky over approximately 26,000 years. This phenomenon, called axial precession, means that Polaris will gradually drift from its position as the pole star. In 1,000 years, the shift is small but measurable. Ancient navigational charts would require adjustment. The constellations maintain their familiar patterns, but their positions relative to the celestial poles change with geological patience. This serves as a reminder that even the seemingly eternal sky is subject to slow transformation. Nothing in the universe is truly fixed. Everything participates in various cycles of change, some fast enough to observe in a human lifetime, others so slow they require instruments and mathematics to detect. The next 1,000 years represent the last period in which Earth would be recognizable to someone from the present. The continents occupy the same positions. The major geological features remain intact. But the surface details, the thin layer of human modification, begin their inevitable dissolution. In 50,000 years, one of Earth's most iconic natural features will cease to exist. Niagara Falls, the massive waterfall system between Lake Erie and Lake Ontario, has been eroding upstream since its formation approximately 12,000 years ago at the end of the last ice age. The falls erode backward at a rate of approximately 1 meter per year, though this rate varies depending on water flow and rock composition. The process is straightforward. Water flowing over the falls erodes the softer rock layers beneath the harder caprock. This creates an overhang, which eventually collapses under its own weight. The falls then retreat upstream, leaving a gorge behind. This process has already moved the falls approximately 11 kilometers from their original position. In another 50,000 years, the falls will have eroded all the way back to Lake Erie. When this happens, the falls will cease to exist as a distinct feature. The water from Lake Erie will flow into Lake Ontario through a river system, but the dramatic drop will be gone. The gorge will remain as evidence of the fall's former existence, a scar in the landscape recording the patient work of flowing water over geological time. This same period will see another subtle but significant change to Earth itself. The planet's rotation is gradually slowing due to tidal friction. The Moon's gravitational pull creates tidal bulges in Earth's oceans. As the planet rotates beneath these bulges, friction converts rotational energy into heat. This energy loss causes Earth's rotation to slow at a rate of approximately 1.7 milliseconds per century. Over 50,000 years, this accumulates to nearly 1 second of additional length to each day. The change is imperceptible on human timescales, but significant over geological periods. Early in Earth's history, days were much shorter. In the distant future, they will be longer still. This slowing also affects the Moon, which gradually moves farther from Earth as the system exchanges angular momentum. These changes illustrate a fundamental principle of the universe. Energy and momentum are conserved, but they transform and redistribute. Systems evolve toward states of lower energy. Friction converts organized motion into random thermal motion. The universe trends toward equilibrium, toward states where nothing interesting happens because all the available energy has been evenly distributed. Earth's slowing rotation and the Moon's recession are small examples of this universal principle. In 100,000 years, the night sky will have transformed in ways that would disorient any observer from the present era. The constellations, those familiar patterns that have guided navigation and inspired mythology throughout human history, are not fixed structures. They are temporary alignments of stars that happen to lie in similar directions from Earth's perspective, but which exist at vastly different distances and move through space at different velocities. Each star in the night sky has its own trajectory through the galaxy. These movements, called proper motions, are generally too slow to notice within a human lifetime. But over 100,000 years, they accumulate into significant changes. The Big Dipper, one of the most recognizable patterns in the northern sky, will be unrecognizable. The stars that form its distinctive shape will have drifted apart. Some will have moved closer together from Earth's perspective, others farther apart. The pattern that has existed for thousands of years will dissolve. Orion, the Hunter constellation visible from most of Earth's surface, will similarly transform. The three stars of Orion's belt will no longer form a straight line. Betelgeuse and Rigel, the bright stars marking the Hunter's shoulder and foot, will have shifted positions relative to the other stars in the pattern. The constellation will require a different interpretation, a different story to explain its shape. This transformation affects all constellations: the Southern Cross, Cassiopeia, Leo, Scorpius, every familiar pattern will have changed. Future observers will create new constellations from the rearranged stars, new stories to explain the patterns they see. The mythology of the sky will be rewritten by the simple fact of stellar motion. This change serves as a reminder of perspective. The constellations seem eternal because they change so slowly relative to human lifespans. But they are temporary arrangements, no more permanent than clouds that happen to resemble familiar shapes. The stars themselves are ancient and long-lived, but their apparent relationships to each other are fleeting when viewed on astronomical timescales. The galaxy rotates, stars orbit the galactic center at different speeds depending on their distance from it, and the patterns we see are snapshots of a dynamic system in constant motion. 100,000 years is sufficient time for these motions to become obvious. It is a blink of an eye in cosmic terms, but long enough to erase the familiar sky. In 1,000,000 years, the last remnants of human construction will have returned to the geological record. The Great Pyramid of Giza, built approximately 4,500 years ago, has survived remarkably well due to its massive scale and the dry climate of its location. But even limestone blocks weighing several tons are not immune to erosion. Wind-blown sand acts as an abrasive, slowly wearing away exposed surfaces. Temperature fluctuations cause expansion and contraction, creating microscopic cracks that gradually widen. Rare rainfall, when it occurs, dissolves small amounts of the limestone, carrying it away in solution. The process is extraordinarily slow, but it is relentless. Over 1,000,000 years, even the most massive stone structures will erode into unrecognizable mounds, then into scattered rubble, then into sediment indistinguishable from the surrounding geology. The pyramids will become part of the desert they sit on, their precise geometry lost to the patient work of natural forces. Meanwhile, beyond Earth's atmosphere, another set of human artifacts faces its own form of erosion. The footprints left by Apollo astronauts on the moon's surface have remained pristine for decades because the moon has no atmosphere, no wind or water to disturb them. But the moon is not a completely static environment. Micrometeorites constantly bombard its surface. These tiny particles, most smaller than a grain of sand, strike the lunar surface at velocities of several kilometers per second. Each impact vaporizes a small amount of material and creates a microscopic crater. Over time, this process, called space weathering, slowly churns the lunar surface. The top layer of lunar soil, called regolith, is gradually mixed and turned over. The rate is extremely slow, measured in millimeters per million years, but it is sufficient. Over 1,000,000 years, the micrometeorite bombardment will have erased the Apollo footprints, filled in the shallow impressions left by astronaut boots, and smoothed the disturbed areas around the landing sites. The artifacts themselves, the descent stages of the lunar modules, and the flags and equipment left behind will remain for much longer. But they too will gradually accumulate micrometeorite damage, their surfaces pitted and degraded by countless tiny impacts. 1,000,000 years demonstrates the difference between human timescales and geological ones. Civilizations rise and fall in thousands of years. Monuments last for tens of thousands. But geological processes operate over millions and billions of years, and on those timescales, even the most durable human constructions are temporary features, brief disturbances in the slow transformation of planetary surfaces. In 50 million years, Earth's geography will have undergone a fundamental transformation. The continents, which appear fixed on human timescales, are in constant motion. They ride on tectonic plates that float on the semi-molten mantle beneath Earth's crust. These plates move at rates of a few centimeters per year, about as fast as fingernails grow. The movement is imperceptible in daily life, but dramatic over geological time. The African plate is moving northward relative to the Eurasian plate at approximately 2 to 3 centimeters per year. This motion is gradually closing the Mediterranean Sea. The process has been ongoing for millions of years and will continue for millions more. In 50 million years, Africa will have collided with Europe. The Mediterranean Sea will have been compressed out of existence, its former basin uplifted and deformed by the collision. This process has precedent. The Himalayas formed when the Indian plate collided with the Eurasian plate approximately 50 million years ago. That collision continues today, pushing the Himalayas higher even as erosion wears them down. The Africa-Europe collision will create a new mountain range, possibly rivaling the Himalayas in scale. The Alps, already formed by earlier phases of this collision, will be incorporated into the larger mountain system. The geography of southern Europe and northern Africa will be completely transformed. Meanwhile, other plate boundaries will have shifted. The Atlantic Ocean will be wider as the Americas continue to drift away from Europe and Africa. The Pacific Ocean will be smaller. Australia will have moved northward, possibly colliding with Southeast Asia. The exact configuration depends on the complex interactions of multiple plates, but the overall pattern is clear. The map of Earth is constantly being redrawn by plate tectonics. 50 million years is a typical timescale for major continental rearrangements. It is long enough for an ocean basin to open or close, for mountain ranges to rise and be partially eroded away, for coastlines to be completely redrawn, yet it is short compared to the age of Earth itself, which is approximately 4.5 billion years. Earth has undergone many cycles of continental assembly and breakup. Supercontinents form when the continents drift together, then break apart as new rifts open. The most recent supercontinent, Pangaea, broke apart approximately 200 million years ago. Before Pangaea, there was Rodinia, and before Rodinia, others whose names and configurations are less certain. In 50 million years, Earth will be in a different phase of this cycle. The continents arranged in a configuration that would be unfamiliar to present-day observers. The transformation happens silently, without drama, driven by the slow convection of the mantle beneath the crust. In 600 million years, a fundamental change will occur in Earth's biosphere. The Sun, like all main sequence stars, gradually increases in luminosity over its lifetime. This happens because as hydrogen fuses into helium in the Sun's core, the core becomes denser. The increased density causes the core to heat up, which increases the rate of fusion, which increases the Sun's energy output. The effect is gradual, approximately 10% per billion years, but its consequences are profound. As the Sun brightens, Earth receives more solar radiation. The planet's temperature increases. This triggers feedback mechanisms in the climate system. Higher temperatures increase the rate of chemical weathering of rocks, which removes carbon dioxide from the atmosphere. This might seem like it would cool the planet, but the process has limits. Plants use carbon dioxide for photosynthesis. As atmospheric carbon dioxide levels drop, photosynthesis becomes more difficult. There are different types of photosynthesis. C4 photosynthesis, used by some grasses and crops like corn, is more efficient at low carbon dioxide concentrations. But the more common C3 photosynthesis, used by most plants including trees, requires higher carbon dioxide levels to function efficiently. In 600 million years, the combination of increased solar radiation and decreased atmospheric carbon dioxide will cross a critical threshold. Carbon dioxide levels will drop below the minimum required for C3 photosynthesis. Most plant species will be unable to survive. The forests will die, the grasslands will die, photosynthetic plankton in the oceans will die. The process will not be instantaneous, but on geological timescales it will be rapid. The biosphere will collapse from the bottom of the food chain upward. Without plants to produce oxygen and serve as the base of the food web, complex life cannot survive. Some organisms may persist in specialized niches. Bacteria that do not require photosynthesis, deep-sea organisms that rely on chemosynthesis rather than photosynthesis may continue. But the rich diversity of life that has characterized Earth for hundreds of millions of years will end. The planet will transition from a living world to a barren one. The oceans will still exist at this point, but they will be largely lifeless. The atmosphere will be different, depleted of oxygen as the existing oxygen reacts with surface rocks and is not replenished by photosynthesis. The planet will still have weather, clouds, rain, but it will be a sterile world, more similar to the early Earth before life arose than to the vibrant biosphere of the present. This marks the end of the habitable phase of Earth's existence. The planet will continue to exist for billions of years beyond this point, but it will no longer support the kind of complex life that has evolved over the past several 100 million years. In 1 billion years, Earth will have lost its oceans. The process begins with the increased solar radiation from the brightening sun. As the planet's surface temperature rises, the rate of evaporation from the oceans increases. More water vapor enters the atmosphere. Water vapor is itself a greenhouse gas, more effective at trapping heat than carbon dioxide. This creates a feedback loop. More heat causes more evaporation, which causes more greenhouse warming, which causes more evaporation. The process accelerates. The atmosphere becomes thick with water vapor. Surface temperatures rise to several hundred degrees. The oceans boil. The planet enters a runaway greenhouse state, similar to the current conditions on Venus. In the upper atmosphere, ultraviolet radiation from the sun breaks apart water molecules. The process, called photodissociation, splits H2O into hydrogen and oxygen. The hydrogen, being very light, escapes Earth's gravity and is lost to space. The oxygen reacts with surface rocks, forming oxides. Over hundreds of millions of years, Earth loses its water. The process is irreversible on planetary timescales. Once the hydrogen is lost to space, the water cannot be reconstituted. By 1 billion years from now, Earth will be a dry, hot planet. The surface will be rock and sand, baked under an increasingly bright sun. The atmosphere will be thick with carbon dioxide and nitrogen, but depleted of water vapor because there is no longer liquid water to evaporate. The temperature at the surface will be incompatible with any known form of life. The planet will resemble Venus, though not quite as extreme. Venus lost its water billions of years ago through a similar process and now has a surface temperature of approximately 460 degrees Celsius. Earth will not become quite that hot, but it will be far too hot for liquid water to exist on the surface. Any remaining water will be locked in minerals deep underground, chemically bound in hydrated rocks. The transformation from a blue planet with liquid water oceans to a dry, barren world represents one of the most significant transitions in Earth's future history. Water has been present on Earth's surface for most of the planet's existence, perhaps as long as 4 billion years. It has shaped the geology, the climate, and the evolution of life. A waterless Earth is a fundamentally different planet, unable to support the kind of chemistry that makes life possible. This future is not unique to Earth. Any planet in the habitable zone of a main sequence star will eventually suffer the same fate as the star brightens with age. The habitable zone itself moves outward over time. Earth, currently in the middle of the Sun's habitable zone, will find itself too close to the Sun to maintain liquid water. The outer planet's moons, currently frozen, will eventually receive enough heat to potentially develop liquid water oceans, though this will be temporary as the Sun continues to evolve. In 4 billion years, the night sky will undergo a dramatic transformation. The Andromeda Galaxy, the nearest large galaxy to the Milky Way, is currently approaching at approximately 110 kilometers per second. This motion is unusual in an expanding universe where most galaxies are receding from each other. Andromeda and the Milky Way are part of the same gravitationally bound group, and their mutual gravity is pulling them together. In 4 billion years, the two galaxies will collide. The term collision is somewhat misleading. Galaxies are mostly empty space. Stars are separated by vast distances relative to their sizes. When two galaxies merge, the stars themselves almost never collide. Instead, they pass by each other, their orbits altered by the changing gravitational field. The process is not violent in the sense of physical impacts, but it is dramatic in terms of the large-scale structure. As the galaxies interpenetrate, their shapes become distorted. The orderly spiral structures of both galaxies are disrupted. Stars are flung into new orbits. Some are ejected from the merged system entirely, becoming intergalactic wanderers. Others are drawn toward the center of the new combined galaxy. The supermassive black holes at the centers of both galaxies, each containing millions of solar masses, will eventually merge into a single, larger black hole. The merger process takes hundreds of millions of years. The galaxies will pass through each other, then fall back together, then pass through again, gradually losing energy to gravitational interactions until they settle into a single structure. The result is an elliptical galaxy, lacking the spiral arms of the original galaxies. Astronomers have named this future galaxy Milkdromeda. From Earth's perspective, if the planet still exists and has observers, the night sky during the merger will be spectacular. Instead of the faint band of the Milky Way, the sky will be filled with stars. New star formation will be triggered as gas clouds collide and compress. Bright young stars will illuminate the sky. The view will be far more dramatic than anything visible from Earth in the present era. However, Earth itself may not survive to see this. The gravitational perturbations from the merger could alter Earth's orbit, potentially ejecting it from the solar system or sending it into the Sun. The Sun's position in the galaxy will certainly change. It might end up in a different part of the merged galaxy, in an orbit that brings it closer to or farther from the galactic center. The merger of the Milky Way and Andromeda is part of a larger pattern. In an expanding universe dominated by dark energy, most galaxies are moving away from each other, and this expansion is accelerating. But within gravitationally bound groups, galaxies can still merge. The local group, which includes the Milky Way, Andromeda, and several smaller galaxies, will eventually merge into a single large galaxy. This will be one of the last major events in the local universe before cosmic expansion isolates the merged galaxy from all others. In 5 billion years, the Sun will reach the end of its main sequence lifetime. For approximately 10 billion years, the Sun has been fusing hydrogen into helium in its core. This process releases energy that creates the outward pressure supporting the Sun against gravitational collapse. But the hydrogen fuel in the core is finite. In 5 billion years, the core will have converted most of its hydrogen into helium. When the hydrogen in the core is exhausted, fusion stops. Without the outward pressure from fusion, the core begins to contract under its own gravity. This contraction heats the core. Eventually, the temperature becomes high enough for hydrogen fusion to begin in a shell surrounding the core. This shell fusion releases more energy than the core fusion did. The increased energy output causes the Sun's outer layers to expand dramatically. The Sun becomes a red giant. Over a period of several 100 million years, the Sun will expand to approximately 100 times its current diameter. The surface will cool, giving the Sun a reddish color, but the total energy output will increase dramatically. The expansion will engulf the inner planets. Mercury, the closest planet to the Sun, will be the first to be consumed. The Sun's expanding atmosphere will reach Mercury's orbit, and the planet will spiral inward due to drag from the Sun's outer layers. It will eventually vaporize in the Sun's interior. Venus will suffer the same fate. Earth's fate is less certain. The Sun's expansion will bring its surface close to Earth's orbit. Some models suggest Earth will be engulfed. Others suggest that the Sun will lose enough mass during the red giant phase that Earth's orbit will expand slightly, keeping it just outside the Sun's surface. Either way, Earth will be uninhabitable. Even if the planet itself survives, the heat from the nearby Sun will be intense enough to vaporize any remaining rocks on the surface. The temperature will be thousands of degrees. Earth, if it exists at all, will be a molten ball of lava orbiting inside or just outside the Sun's outer atmosphere. The red giant phase is unstable. The Sun will pulsate, expanding and contracting over periods of thousands of years. With each pulsation, it will lose mass as its outer layers are blown off into space. The Sun will lose approximately half of its mass during the red giant phase. This lost material will form a shell of gas expanding away from the Sun. The Sun's core, meanwhile, continues to contract and heat up. Eventually, the temperature becomes high enough for helium fusion to begin. Helium fuses into carbon and oxygen. This helium fusion phase is shorter than the hydrogen fusion phase, lasting only about 100 million years. When the helium in the core is exhausted, the Sun will again expand, becoming even larger. But the Sun's mass is too low for the core to reach the temperatures required for carbon fusion. The Sun will never progress beyond helium fusion. This sets the stage for the next phase of the Sun's evolution. In 7 billion years, the Sun will shed its outer layers and create a planetary nebula. This is not an explosion like a supernova. It is a gentler process, though still dramatic by human standards. The Sun, having exhausted its helium fuel, can no longer sustain fusion in its core. The core contracts and heats up, but never reaches the temperature required for carbon fusion. The outer layers, no longer supported by fusion energy, are loosely bound to the core. The Sun pulsates strongly, and with each pulsation, more material is ejected. Strong stellar winds blow the outer layers away from the core. Over tens of thousands of years, the Sun loses its entire outer envelope. The ejected material forms an expanding shell of gas surrounding the core. This shell is the planetary nebula. The name is historical and misleading. Planetary nebulae have nothing to do with planets. Early astronomers thought they looked like planets through small telescopes, hence the name. The nebula is illuminated by ultraviolet radiation from the hot core. The gas glows in characteristic colors determined by its composition. Hydrogen emits red light, oxygen emits green and blue, nitrogen emits red. The result is a beautiful, colorful structure. Planetary nebulae come in many shapes. Some are spherical, others bipolar with 2 lobes, others more irregular. The shape depends on the star's rotation, magnetic field, and whether it has a companion star. The Sun's planetary nebula will likely be relatively simple, probably spherical or slightly elliptical. The nebula will expand at approximately 20 kilometers per second. Over tens of thousands of years, it will grow to several light years in diameter. The gas will gradually disperse into the interstellar medium, enriching it with the heavier elements created in the Sun's interior. This material will eventually be incorporated into new stars and planets, continuing the cycle of stellar birth and death. At the center of the nebula, the Sun's core remains. It is no longer generating energy through fusion. It is simply a hot, dense ball of carbon and oxygen, approximately the size of Earth, but with about half the Sun's original mass. This is a white dwarf star. The white dwarf is incredibly dense. A teaspoon of white dwarf material would weigh several tons on Earth. The matter is in a degenerate state, supported against further collapse by electron degeneracy pressure, a quantum mechanical effect. The white dwarf is initially very hot, with a surface temperature of approximately 100,000 degrees Celsius. It glows with intense ultraviolet and visible light, but it has no internal energy source. It can only cool by radiating its stored thermal energy into space. This cooling process is extremely slow, taking billions of years. The planetary nebula phase lasts only tens of thousands of years. The nebula expands and disperses, gradually fading from view. Eventually, only the white dwarf remains, slowly cooling in the darkness. This is the final stable state for stars like the Sun. More massive stars end as neutron stars or black holes after supernova explosions, but stars with masses similar to the Sun become white dwarfs. The white dwarf will continue to cool for trillions of years, eventually becoming a black dwarf, a cold, dark cinder in space. In 100 billion years, the universe will have changed in a profound and unsettling way. The expansion of the universe, driven by dark energy, will have carried distant galaxies beyond the cosmic horizon. Light from these galaxies will no longer be able to reach our location. They will effectively disappear from the observable universe. This is not because they have been destroyed, but because the space between us and them is expanding faster than light can travel through it. The effect is gradual, but inexorable. Currently, astronomers can observe galaxies billions of light years away. The most distant galaxies visible today are seen as they were more than 13 billion years ago, when the universe was young. But as the universe continues to expand and the expansion accelerates, these distant galaxies fade and redshift until their light becomes undetectable. The cosmic horizon shrinks. In 100 billion years, only the galaxies in the local group will remain visible. The local group consists of the Milky Way, Andromeda, and several dozen smaller galaxies, all gravitationally bound together. By this time, they will have merged into a single, large elliptical galaxy. This merged galaxy will be surrounded by darkness. An astronomer in this future era, looking out into space, would see only their own galaxy. The rest of the universe would be invisible, not because it does not exist, but because its light can no longer reach the observer. The cosmic microwave background radiation, the afterglow of the Big Bang that currently fills the sky, will have redshifted into undetectability. The evidence that the universe began in a hot, dense state will have been erased by expansion. This has philosophical implications. Astronomers in that distant era, if they exist, will not be able to reconstruct the history of the universe in the way that present-day astronomers can. They will see a static, apparently eternal galaxy surrounded by empty space. They will have no evidence of the Big Bang, no evidence that the universe is expanding, no evidence that other galaxies ever existed. The universe will appear fundamentally different to them than it does to present-day observers. This illustrates a troubling aspect of cosmology. The universe we can observe depends on when we observe it. The evidence available to astronomers changes over cosmic time. Some information becomes inaccessible as the universe ages. Future observers will be unable to discover certain truths about the universe's history because the evidence will no longer exist in an observable form. 100 billion years also marks a transition in the universe's stellar population. The universe is approximately 13.8 billion years old currently. In another 100 billion years, it will be more than 7 times older. Most of the stars that exist now will have died. The longest-lived stars, small red dwarfs with masses less than half that of the Sun, can live for trillions of years. But the larger, brighter stars that dominate the night sky in the current era will all be gone. The universe will be darker, populated by faint red dwarfs and the remnants of dead stars. In 1 trillion years, the universe will have entered a new era. Star formation, the process that has populated the universe with luminous objects for billions of years, will be ending. Stars form from clouds of gas and dust in galaxies. Gravity causes these clouds to collapse, and as they collapse, they heat up. When the center of a collapsing cloud reaches approximately 10 million degrees, hydrogen fusion ignites and a new star is born. This process requires a supply of gas. Galaxies contain vast reservoirs of hydrogen gas, the raw material for star formation. But this supply is not infinite. Each generation of stars locks up some of this gas in long-lived stars and stellar remnants. Some gas is ejected from galaxies by supernova explosions and stellar winds. The overall trend is toward depletion. In 1 trillion years, the gas reservoirs in galaxies will be largely exhausted. The rate of star formation will have declined to a tiny fraction of its current value. The universe will still contain stars, but they will be the long-lived red dwarfs formed earlier. No new massive stars will be born. The universe will be in the late stages of its stelliferous era, the age of stars. This has profound implications for the universe's appearance. Currently, galaxies are bright because they contain many massive luminous stars. These stars are short-lived, lasting only millions to tens of millions of years, but they are constantly being replaced by new star formation. When star formation ends, these bright stars will disappear and not be replaced. Galaxies will fade as their stellar populations age and die. The universe will become darker. The only stars that remain will be red dwarfs, which are very faint. A red dwarf with 1/10 the sun's mass emits only about 1/1000th of the sun's light. Even though red dwarfs are the most common type of star, they contribute relatively little to the total light output of galaxies. A galaxy full of red dwarfs would be much dimmer than a galaxy with active star formation. In 1 trillion years, the universe will be populated by dim, aging galaxies. The vibrant star-forming regions that characterize young galaxies will be absent. The universe will have entered a quieter, darker phase. This transition is gradual but inevitable. It is driven by the finite supply of gas and the one-way conversion of that gas into stars and stellar remnants. 1 trillion years may seem like an incomprehensibly long time, but it is short compared to the ultimate lifespan of the universe. Red dwarf stars, the smallest and longest-lived stars, can burn for 10 trillion years or more. Even after star formation ends, the universe will remain illuminated by these faint stars for many trillions of years. But the trend is clear. The universe is aging. It is transitioning from a bright, active state to a dim, quiet state. This is not a sudden catastrophe, but a gradual decline, a slow fading as the energy sources that power luminous objects are depleted. In 100 trillion years, the last ordinary star will burn out. The stelliferous era, the age during which the universe is populated by stars undergoing nuclear fusion, will come to an end. This marks one of the most significant transitions in cosmic history. For approximately 100 trillion years, the universe will have been illuminated by stars, but that era will now be over. The last stars to die will be the smallest red dwarfs, stars with masses less than 1/10 that of the Sun. These stars burn their hydrogen fuel extremely slowly, which allows them to live for trillions of years. But even they are not eternal. Eventually, they exhaust their hydrogen, fusion stops, and they cool into white dwarfs. When the last red dwarf dies, the universe will go dark. There will be no more nuclear fusion occurring in ordinary stars. The only sources of light will be the fading remnants of dead stars, white dwarfs, neutron stars, and the accretion disks around black holes. White dwarfs are the most common stellar remnants. They are the cores of former stars, no longer undergoing fusion, simply cooling by radiating their stored thermal energy. When a star like the Sun dies, it leaves behind a white dwarf with approximately half the Sun's mass compressed into a sphere about the size of Earth. In 100 trillion years, the universe will contain countless white dwarfs, all slowly cooling. The cooling process is extremely slow. A white dwarf starts with a surface temperature of approximately 100,000 degrees Celsius. It cools to 10,000 degrees over approximately 1 billion years, then continues to cool more slowly. After 100 trillion years, many white dwarfs will have cooled to temperatures of a few thousand degrees. They will emit a faint red glow, barely visible. The universe will be lit by these dim embers. Neutron stars, the remnants of more massive stars, will also be present. They too will be cooling, though they start from even higher temperatures and cool even more slowly than white dwarfs. Some neutron stars are pulsars, emitting beams of radiation that sweep across space like lighthouse beams. But pulsar emission is powered by the neutron star's rotation, and rotation slows over time due to energy loss. After 100 trillion years, most pulsars will have spun down and become inactive. Black holes will also populate the universe. They emit no light of their own, but if they have material falling into them, that material forms an accretion disk that heats up and emits radiation. However, in 100 trillion years, most black holes will be isolated, with no nearby material to accrete. They will be invisible, detectable only by their gravitational effects. The universe in 100 trillion years will be a cold, dark place. The temperature of space itself will have dropped to a fraction of a degree above absolute zero. The cosmic microwave background, currently at 2.7 Kelvin, will have cooled to an imperceptible whisper. Any observers in this era would find themselves in a universe vastly different from the one we know. The bright galaxies full of stars will be gone, replaced by diffuse collections of stellar remnants. The universe will have entered what cosmologists call the degenerate era, dominated by degenerate matter in the form of white dwarfs and neutron stars. In 1 quadrillion years, the gravitational structure of the universe will have decayed significantly. Galaxies, which currently exist as bound systems with stars orbiting a common center, will have largely dissolved. This process is driven by gravitational interactions between stars and stellar remnants. When two objects pass close to each other, they exchange energy through gravitational interaction. Sometimes both objects remain bound to the galaxy, but in altered orbits. Sometimes one object gains enough energy to escape the galaxy entirely, while the other falls deeper into the gravitational well. Over extremely long timescales, these interactions cause galaxies to evaporate. The process is analogous to the evaporation of a liquid. In a liquid, molecules have a range of velocities. Occasionally, a molecule near the surface has enough velocity to escape the liquid's gravitational attraction. Over time, the liquid evaporates. Similarly, in a galaxy, stars occasionally gain enough velocity through gravitational interactions to escape. The galaxy slowly loses mass. In 1 quadrillion years, most stars and stellar remnants will have been ejected from their host galaxies. They will wander through intergalactic space as isolated objects. The galaxy as a coherent structure will have dissolved. What remains will be a diffuse halo of objects, no longer orbiting in any organized way. Some objects will not be ejected, but will instead fall toward the galactic center. Galaxies contain supermassive black holes at their centers, with masses ranging from millions to billions of times the Sun's mass. As stars and stellar remnants interact gravitationally, some lose energy and spiral inward. Over quadrillions of years, a significant fraction of a galaxy's mass will be consumed by the central black hole. The black hole will grow larger as it accretes this material. The final state of a galaxy, after quadrillions of years of evolution, will be a supermassive black hole surrounded by a sparse halo of escaped stellar remnants. The organized structure of the galaxy will be gone. The universe will consist of isolated objects, white dwarfs, neutron stars, and black holes, most of them wandering alone through space, no longer part of any larger structure. Occasionally, two of these objects will encounter each other. If they pass close enough, they might form a binary system, orbiting each other. More often, they will simply pass by, their trajectories slightly altered by the encounter. The universe will be a lonely place, with vast distances between objects. The density of matter will be extremely low. Space will be dark and cold. The only events of note will be rare gravitational encounters between isolated objects. This marks the transition from the degenerate era to what comes next. The organized structures of the universe, from planets to solar systems to galaxies, will have dissolved. What remains is a collection of individual objects, each following its own trajectory through an expanding, cooling universe. In 10 to the 30th power years, matter itself may begin to decay. This is a speculative prediction based on certain theories in particle physics, but it represents a fundamental change in the nature of the universe. Ordinary matter consists of atoms, which are made of protons, neutrons, and electrons. Protons and neutrons are in turn made of quarks held together by the strong nuclear force. The question of proton decay is one of the major unsolved problems in physics, with implications for the ultimate fate of matter in the universe. In the current understanding of physics, protons are stable. They do not decay. However, some grand unified theories predict that protons are not absolutely stable, but decay with an extremely long half-life, possibly around 10 to the 34th power years. If proton decay occurs, it would have profound consequences. A proton decays into lighter particles, typically a positron and a neutral pion, which then decays into gamma rays. The mass of the proton is converted into energy according to Einstein's equation. Over timescales of 10 to the 30th power years, a significant fraction of the protons in the universe would have decayed. This means that the white dwarfs and neutron stars that populate the universe would gradually dissolve. White dwarfs are made primarily of carbon and oxygen nuclei, which contain protons. As those protons decay, the white dwarf loses mass and emits radiation. Eventually, the white dwarf would evaporate entirely, leaving only the energy released by proton decay. Neutron stars are more complex. They are made primarily of neutrons, which are stable in free space, but only because they decay into protons, electrons, and antineutrinos with a half-life of about 15 minutes. Inside a neutron star, neutrons are stabilized by the extreme density and pressure. But if protons decay, the protons that exist in equilibrium with neutrons in the neutron star will decay, disrupting the equilibrium. The neutron star would gradually dissolve, though the process is complicated by the extreme conditions. Even black holes would be affected indirectly. Black holes do not contain matter in the ordinary sense. The matter that falls into a black hole is crushed beyond recognition. But if the universe around black holes consists of decaying matter, the black holes will be the only remaining massive objects. The universe in 10 to the 30th power years, if proton decay occurs, would be fundamentally different from anything that came before. There would be no atoms, no nuclei, no ordinary matter. The universe would consist of radiation, light particles like electrons and positrons, neutrinos, and black holes. The concept of solid objects would be meaningless because there would be no matter to form them. It is important to note that proton decay has never been observed. Experiments have placed lower limits on the proton half-life of more than 10 to the 34th power years, but they have not detected any decays. It is possible that protons are absolutely stable and do not decay at all. If that is the case, white dwarfs and neutron stars would persist indefinitely, cooling but never dissolving. In 10 to the 40th power years, the universe will have entered the black hole era. If proton decay has occurred, ordinary matter will have largely disappeared, dissolved into radiation and light particles. The dominant massive objects in the universe will be black holes. The complex hierarchy of structures that characterizes the current universe, from planets to stars to galaxies, will be gone. What remains is a sparse distribution of black holes, slowly evaporating in an expanding, cooling universe. Black holes are regions of space-time where gravity is so strong that nothing, not even light, can escape from within the event horizon. They form when massive stars collapse at the end of their lives, or when matter accumulates and collapses under its own gravity. The universe contains black holes of many sizes. Stellar mass black holes, with masses of a few to a few hundred times the Sun's mass, form from individual stars. Intermediate mass black holes, with masses of hundreds to thousands of solar masses, may form from clusters of stars. Supermassive black holes, with masses of millions to billions of solar masses, reside at the centers of galaxies. In 10 to the 40th power years, these black holes will be the primary remaining structures in the universe. They will be isolated, separated by vast distances in an expanding universe. The space between them will be nearly empty, containing only sparse radiation and light particles. Black holes are not entirely black. Stephen Hawking showed in 1974 that black holes emit radiation due to quantum effects near the event horizon. This Hawking radiation causes black holes to lose mass over time. The rate of mass loss is inversely proportional to the black hole's mass. Small black holes evaporate quickly, while large black holes evaporate very slowly. A black hole with the mass of the Sun would take approximately 10 to the 67th power years to evaporate completely. Supermassive black holes with billions of solar masses would take even longer, around 10 to the 100th power years. But eventually, all black holes will evaporate. The black hole era is the period during which black holes are the dominant objects in the universe, but even they are temporary. The universe in this era will be extraordinarily empty and dark. Black holes emit Hawking radiation, but for large black holes, this radiation is extremely faint. A solar mass black hole emits radiation at a temperature of approximately 1/10,000,000th of a Kelvin, far colder than the cosmic microwave background in the current era. The radiation is so faint that it would be essentially undetectable. The universe will be cold, dark, and nearly featureless. The only significant events will be the occasional evaporation of a black hole, releasing a burst of radiation as the black hole finally disappears. But these events will be separated by vast spans of time and space. The black hole era represents a phase of the universe in which structure has almost entirely disappeared. In 10 to the 60th power years, even stellar mass black holes will have begun to evaporate significantly through Hawking radiation. The process is extremely slow, but over these vast timescales, it becomes the dominant phenomenon. Hawking radiation arises from quantum effects near a black hole's event horizon. Virtual particle-antiparticle pairs constantly appear and annihilate in empty space due to quantum fluctuations. Near a black hole's event horizon, One particle of a pair can fall into the black hole while the other escapes. To an outside observer, it appears that the black hole is emitting radiation. This radiation carries energy away from the black hole, causing it to lose mass. The rate of evaporation increases as the black hole becomes smaller. A smaller black hole has a higher temperature and emits more radiation. As the black hole loses mass, its temperature increases, causing it to evaporate faster. The process accelerates in a runaway feedback loop. The final stages of black hole evaporation are dramatic. As the black hole shrinks to a tiny mass, its temperature becomes extremely high. It emits intense radiation across the entire electromagnetic spectrum. Finally, when the black hole reaches approximately the Planck mass, it evaporates in a final burst of energy. The timescale for this process depends on the black hole's initial mass. A black hole with the mass of the Sun requires approximately 10 to the 67th power years to evaporate completely. Smaller black holes evaporate faster, larger ones slower. By 10 to the 60th power years, black holes with masses less than a few times the Sun's mass will have evaporated. The universe will still contain larger black holes, but the smallest ones will be gone. The evaporation of black holes represents the final conversion of mass into energy. The black hole's mass, concentrated in an infinitesimally small region of space, is converted into radiation that spreads out into the universe. This radiation contributes to the thermal energy of the universe, but it is spread so thinly that it has negligible effect on the universe's temperature. The universe will remain extremely cold, with temperatures far below 1 Kelvin. The radiation from evaporating black holes will be diluted by the expansion of space, becoming ever more diffuse. By 10 to the 60th power years, the universe will be transitioning from the black hole era to the final era. Most stellar mass black holes will have evaporated or will be in the late stages of evaporation. Only the supermassive black holes will remain, and even they will be slowly losing mass to Hawking radiation. The universe will be approaching a state where even black holes, the last remaining structures, will have disappeared. In 10 to the 100th power years, even the largest supermassive black holes will have evaporated. These black holes, with masses of billions of times the Sun's mass, are the longest-lived objects in the universe. But even they cannot escape the slow drain of Hawking radiation. The evaporation of a supermassive black hole takes an almost incomprehensible length of time. A black hole with 10 billion solar masses requires approximately 10 to the 100th power years to evaporate completely. The process is so slow that for most of the black hole's lifetime, the evaporation is imperceptible. But eventually, the black hole shrinks to a smaller mass, its temperature increases, and the evaporation accelerates. The final evaporation of a supermassive black hole is the last major event in the universe. As the black hole shrinks, it emits increasing amounts of radiation. In its final moments, when it has shrunk to a tiny fraction of its original mass, it emits intense radiation across all wavelengths. Finally, it disappears in a burst of energy, converting its remaining mass into radiation. This marks the end of the black hole era. After this point, the universe contains no black holes, no stars, no planets, no atoms if proton decay has occurred. All that remains is radiation and possibly some stable elementary particles. The universe has reached a state of maximum entropy. Entropy is a measure of disorder or randomness. The second law of thermodynamics states that entropy always increases in a closed system. The universe has been increasing in entropy since the Big Bang. The early universe was in a low entropy state, with energy concentrated in a hot, dense plasma. As the universe expanded and cooled, structures formed: atoms, stars, galaxies. These structures represent local decreases in entropy. but they are powered by processes that increase the total entropy of the universe. Stars burn fuel, converting low-entropy matter into high-entropy radiation. Black holes represent a temporary storage of entropy, but when they evaporate, they release that entropy back into the universe. By 10 to the 100th power years, all the processes that can increase entropy have run their course. The universe is in a state of thermal equilibrium. There are no temperature differences to drive heat flow, no concentration of energy to power any processes. The universe has reached what is called heat death. This does not mean that the universe is hot. In fact, it is extremely cold, with a temperature approaching absolute zero. Heat death refers to the fact that all the available energy has been evenly distributed. There are no energy gradients, no way to extract useful work from the remaining energy. The universe is in a state of maximum entropy and minimum useful energy. After 10 to the 100th power years, the universe enters its final era. All black holes have evaporated. All matter has either decayed or been converted to energy. What remains is a thin sea of photons, neutrinos, and possibly electrons and positrons, depending on whether proton decay has occurred. The universe is dominated by radiation. The photons are the remnants of all the processes that occurred throughout cosmic history. They are the light from stars that shone trillions of years ago, redshifted to infinitesimally long wavelengths by the expansion of the universe. They are the Hawking radiation emitted by evaporating black holes. They are the gamma rays produced by proton decay, if that occurred. All of this radiation has been diluted by expansion and cooled to temperatures unimaginably close to absolute zero. The wavelength of a typical photon will be larger than the observable universe. The energy per photon will be infinitesimally small. The universe will be cold and dark in any practical sense. The temperature will be so close to absolute zero that the difference is meaningless. There will be no light in any recognizable form, only these ultra-low energy photons. Neutrinos, which interact very weakly with other matter, will also populate the universe. They were produced in vast numbers during the Big Bang and during various stellar processes throughout cosmic history. Like the photons, they will have been cooled and diluted by expansion. If electrons and positrons are stable, they will also be present, but at extremely low densities. The average distance between particles will be enormous, far larger than the current observable universe. Particles will almost never interact with each other. The universe will have reached a state of near-perfect emptiness. This is the Photon Age, also called the Dark Era. It is the final state of the universe according to current physical understanding. The universe will expand forever, becoming ever colder and more dilute. Nothing interesting will happen because there is no energy available to make anything happen. The universe will have reached equilibrium. This state will persist forever. There is no process that can reverse it. The universe cannot collapse back on itself because the expansion is accelerating due to dark energy. It cannot heat up because there are no energy sources remaining. It has reached the end of its evolution. The concept of time becomes somewhat meaningless in this state. Time is measured by change. If nothing changes, if the universe is in a static equilibrium, then, in a sense, time has stopped. Clocks require energy to run, and there is no available energy. Even if there were, there would be nothing for a clock to measure because nothing is happening. This is the ultimate fate of the universe, according to current cosmological models. It is not a dramatic ending, but a gradual fading into darkness and cold. The universe does not end with a bang or a crunch, but with an eternal, unchanging whisper. The final state of the universe is one of perfect equilibrium. This is not a temporary balance, but a permanent condition from which there is no escape. The universe has reached maximum entropy, a state where all energy is evenly distributed and no work can be extracted. In thermodynamics, equilibrium is the state toward which all systems evolve. The universe does not fight its fate. It simply follows the laws of physics to their logical conclusion. The journey from the Big Bang to the final equilibrium takes an almost infinite amount of time, but the destination is inevitable. The universe will rest. A hot object in contact with a cold object will transfer heat until both reach the same temperature. A compressed gas will expand until its pressure equals the surrounding pressure. Systems naturally evolve toward states of higher entropy and lower available energy. The universe is no exception. The universe began in a low entropy state at the Big Bang. The early universe was hot and dense, with energy concentrated in a small volume. As the universe expanded and cooled, this energy spread out. Structure formed through gravitational collapse, creating stars and galaxies. These structures burned fuel, converting low-entropy matter into high-entropy radiation. The process has been ongoing for nearly 14 billion years and will continue for many orders of magnitude longer. But eventually, all the fuel is exhausted, all the stars burn out, all the black holes evaporate, and the universe reaches equilibrium. In this final state, there are no temperature differences anywhere in the universe. The temperature is uniform, infinitesimally close to absolute zero. There are no pressure differences, no concentration of matter, no energy gradients of any kind. The universe is perfectly homogeneous and isotropic at the largest scales. The concept of events ceases to have meaning. An event is a change in the state of a system. But in equilibrium, nothing changes. The universe is static. Particles exist, but they do not interact in any meaningful way. The distances between particles are so vast and their energies so low that interactions are effectively impossible. The universe has become a featureless void. This state is sometimes called the heat death of the universe, though it is more accurately described as a cold death. The term heat death comes from thermodynamics and refers to the death of heat flow, not to high temperatures. In this state, there is no heat flow because there are no temperature differences to drive it. The universe is in thermal equilibrium at a temperature near absolute zero. From a philosophical perspective, this raises questions about the nature of time. Time is often defined by change. If nothing changes, does time still exist? In the equilibrium state, there is no way to distinguish one moment from another. The universe looks the same at all times. In this sense, time becomes meaningless. The universe has reached a state of timelessness. This is the ultimate fate predicted by current cosmological models based on the observed accelerating expansion of the universe. The expansion will continue forever, driven by dark energy. The universe will never recollapse. It will simply expand and cool forever, approaching but never quite reaching absolute zero. The final state is one of maximum entropy and minimum temperature, a universe that is dark, cold, and unchanging for all eternity. It is a peaceful end, if not a particularly interesting one. This has been a journey through the longest story ever told, the complete history of the universe from the present moment to its final state, trillions upon trillions of years in the future. The narrative follows a simple pattern. Time moves forward in ever larger steps. Each chapter marks a milestone in the slow transformation of everything that exists. The pattern is predictable and calming. There are no surprises because the laws of physics determine what must happen. The universe follows these laws with perfect consistency. The story begins with familiar things: Earth, the sun, the stars, and the night sky. These are the anchors that connect the narrative to human experience. But gradually, the perspective expands. The timescales grow longer. The changes become more fundamental. Continents drift and collide. Oceans evaporate. The sun becomes a red giant and then a white dwarf. Galaxies merge. Stars burn out. Black holes evaporate. Matter itself may decay. Finally, the universe reaches a state of perfect equilibrium, cold and dark and unchanging. The journey illustrates several themes. One is the impermanence of all structures. Everything that exists now will eventually be transformed into something else. Mountains erode, stars die, galaxies dissolve. Even atoms may not be permanent. The only constant is change, and that change always moves in the same direction, toward higher entropy and lower available energy. Another theme is the vast difference between human timescales and cosmic ones. Human history spans thousands of years. Geological processes take millions. Stellar evolution takes billions. The heat death of the universe takes googles of years. These numbers are so large they lose intuitive meaning, but they are real. The universe operates on timescales that dwarf human comprehension. A third theme is the inevitability of the ending. The universe is not heading toward some uncertain fate. The laws of physics determine what will happen. The details may vary, but the overall pattern is clear. The universe will expand, cool, and eventually reach equilibrium. There is comfort in this predictability. The universe is not capricious or chaotic. It follows rules, and those rules lead to a peaceful, if cold, conclusion. For those seeking relaxation or sleep, this narrative offers a unique form of comfort. It places human concerns in cosmic context. The anxieties and urgencies of daily life dissolve when viewed against the timescale of the universe. Everything that seems important now will be forgotten long before the sun dies. This is not nihilistic, but liberating. It grants permission to let go, to stop struggling against the inevitable, to rest. The universe itself will eventually rest. Until then, there is this moment, this brief flicker of warmth and light in the long darkness. The journey has ended where it must, in silence and stillness. If this exploration has brought some measure of peace, then it has served its purpose. Rest well.